Assalamualaikum and hi. So today we are going to look at a new chapter, chapter 5, electromagnetic induction. So in this video we're going to look at subtopic 5.1, magnetic flux. There are two learning objectives here. The first one is to define and use magnetic flux and also to use magnetic flux linkage. So what are we going to do here first is to understand what is meant by the term magnetic flux here. Okay, so magnetic flux is a measure of the number of field lines that crosses a cross-sectional area. So field line here refers to the magnetic field lines, and how many field line is going to cross over a certain surface area is what we call the magnetic flux. For example here, so this is our area, and this is our vector of the area, which is the surface of the area. So flux, magnetic flux is a measure of how many magnetic field line that is going to cross this surface area. Okay, or it is also defined as scalar product, which is the dot product between the magnetic flux density B and the vector of the surface area A. So we use this symbol here to represent the magnetic flux. So this is our magnetic flux. Magnetic flux is B dot A, which is BA cos theta. This is the scalar product. Okay, it is a B dot A scalar product. So BA cos theta, B is the magnetic field strength or magnetic flux density. A is the cross-sectional area where the field line that is going to pass through, and then theta here is the angle between B and also the vector A. Okay, magnetic flux is a scalar quantity, which means it does not have any direction, and the unit that we associate for our magnetic flux here is, as we know, flux is BA cos theta. B has a unit of Tesla and area has a unit of meter. So we have a unit of Tesla, meter squared, TM squared, or WB Weber. This is a common unit that we associate to our flux. Alright, so remember that vector A is always normal to the plane of the coil. So this is our plane. This is our plane, and the vector is always 90 degrees. So as you can see here, it is shown in this diagram here. This is the vector and it is perpendicular to the plane here. So as you can see, the area here has field line that passing through the surface. So the angle between B and A is such that the angle from the vector A to the magnetic field line theta. Alright, so let us now consider a uniform magnetic field B passing through a surface area A of a single turn coil as shown in figure 1A and 1B. So what we have here is uniform magnetic field to the right, and we have our plane. This is our plane, which is perpendicular to the magnetic field. Given to us is the plane which is perpendicular to the B. However, we have magnetic flux is given as BA cos theta. Theta here is the angle between B and also vector of the area. Okay, so this perpendicular here is the angle between plane and also the B. So this is not the theta that we want. Theta that we want is from the surface area. This is your surface, perpendicular to your surface, which is what we call as the vector A. As you can see, the plane and the vector A are perpendicular, which is normal to each other always. They are always 90 degrees to each other. So now for our theta here, we want the angle between B and also the vector A. So as you can see, they are parallel to each other. So we'll end up with BA cos 0. Cos 0 gives us 1. So the flux here is BA. Whereas for figure 1b, we have magnetic field to the right and our plane here is now parallel. The plane here is parallel to the B. However, V1 flux here is BA cos theta. Theta is the angle between B and vector A. Vector A is perpendicular to the plane, and also in this case it is perpendicular to the B. They are 90 degree to each other, as you can see. The B and A are 90 degree to each other. So we will have flux here is BA cos 90. Cos 90 is equals to 0. So our flux here is equals to 0. So you will have a maximum flux when the area, vector area and the B are parallel to each other, and you will have them the least or the minimum, which is 0 basically, when they are perpendicular to each other. Okay, next we are going to look at magnetic flux linkage. Okay, what is magnetic flux linkage? For magnetic flux linkage, we associate with the symbol of the flux, put in a bar on top and bottom of your flux, and then put an L subscript here to indicate that this is magnetic flux linkage. So this symbol is what we use to associate magnetic flux. Magnetic flux, however, magnetic flux linkage is this one. Alright, so what is magnetic flux linkage? Okay, when you have magnetic flux through the coil, is magnetic flux through every turn of the coil. Okay, magnetic flux through the coil. So this is your coil. So you're going to have B passing through the area. So this is what we call as the flux. Okay, this flux is going to pass through for every turn of the coil. Let's say your coil here has many turns. The total flux through all the turn of the coil N is called the magnetic flux linkage. So for every single turn, they will have flux. Okay, for every single turn, they will have flux BA cos theta. So for the total coil here, you're going to have n number of turn. So the magnetic flux linkage is basically the total flux for every single turn. Therefore, you have to multiply with the n and the flux for every single turn. So mathematically, as given here, magnetic flux linkage is n multiplied with magnetic flux for each turn, which is NBA, where the unit here is still Weber. The magnetic flux linkage has the same unit as magnetic flux. Cuma the difference between flux linkage dengan magnetic flux adalah magnetic flux untuk setiap pusingan itu. Okay, ada coil itu akan ada banyak number of turn. For one turn, dia akan ada area dia dan dia akan ada B yang passes through. So this is what we call flux. Tapi kalau for many turns, the total of all these turn is what we call it as magnetic flux linkage. Alright,